All right, have you heard this word before? Stoichiometry? Yes, maybe, no, big fancy word. I don't know why we use that word necessarily. It makes everything sound more difficult than it is. It's just a fancy way of saying amounts or mass relationships. How much of this do you need? How much of this do you need? How much of this do you make? That's it. So we're going to look at these mass relationships in the context of chemical equations. This is a really important skill in this class, but also going forward, especially if you're going into any kind of technical field where you need to have certain amounts of things. It doesn't need to be chemical in nature, but you'll need to do these types of adjustments. Even in stuff like cooking, I do these types of calculations all the time. I'm not using moles, obviously, but it's the same kind of idea. All right. So let's look at like our very simple reaction that we started with before, which is hydrogen and oxygen. So hydrogen reacts with oxygen, and we had this issue where we were losing oxygen atoms. So in order to make those equivalent, we had to change the ratio by which they react, or in which they react. So we have 2 hydrogens for every 1 oxygen. And then we kind of made a big deal about that that's a count, that we're counting hydrogens per oxygen or oxygens per hydrogen. We're counting individual molecules, but because these are so tiny, we can't actually physically count the molecules. So what do we do instead? How do we count molecules? In what quantities? In moles, because we can't count the individual ones. We count them by moles instead. Of course, then we also talked about how that presents other problems because we can't count moles in the lab any better than we can count molecules because we still can't count molecules. So we need a way to convert from something we can measure easily to something we can count, which is what we did last week when we talked about going from grams to moles and moles to grams. So now we're going to just do that in the context of a chemical reaction and talk about those ratios. So let's say, and usually this is done like in the forward direction. I want to do it in the backwards direction because that's the more common and more useful way to do it. So let's say we're doing this reaction because we want to make 10 grams, 10.0 grams of hydrogen, or of water. So we're doing a chemical reaction because we want to synthesize something. In this case, we're synthesizing water. We want to make 10 grams of water. So we want to know how much of each of these we need. Just like when you're cooking at home and you want to make 300 cookies and you need to know how much of each ingredient you need to make 300 cookies. If you do make 300 cookies, bring some in so we can have cookies. That's a lot of cookies. All right, so we need to figure out how much of each of those we need. Do we just take like 5 grams of hydrogen and 5 grams of oxygen? Because the masses have to add up, right? Why doesn't that work? Yeah, that's going to give us a different ratio of counting reagents. So it's going to give us a mass ratio that works because we have to have 10 grams total of reactants and 10 grams total of products. But it's not going to tell us how much of each because that's not going to give us the right ratio. So how do we determine the right ratio? We need to go back to accounting. We need to count the water molecules and say, how many water molecules do we need to make? And then we can know how many hydrogen molecules and how many oxygen molecules we need to do that. All right, so to do that, we're going to convert from grams to moles because that's how we count things. So we're going to say 10 grams of water. We're going to multiply that by the molar mass of water, which is 18.0 grams per mole. And that gets us from grams of water to moles of water. So now we know how many moles of water we need for this particular reaction. All right. Once we know how many moles we need, we can figure out how many moles of the other things we need. Because of the mole ratio from the equation. So we know every 2 molecules of water that we make, we need 2 molecules of hydrogen and 1 molecule of oxygen. If we want to do that mathematically, that looks like this. We want to say that we convert from moles of water to moles of one of the other things, let's say hydrogen. And then we can do the other one right underneath it here. Same thing, we start with moles of water, and we convert from moles of water to moles of oxygen. And we pull those numbers directly from the equation to plug in to that conversion. So we've got, the equation tells us that for every 2 of these, we need 2 of those. That for every 2 of these, we need 1 of those. That's what these coefficients that we've worked so hard on balancing our equation can do for us. So once we've plugged those in, 2 over 2 is 1. And this would just be dividing by 2. What would I do here? Okay. So now we know how much of each reactant we need based on moles. So we know that for every 2 moles of water we make, we're going to need 2 moles of hydrogen. For every 2 moles of water we make, we're going to need 1 mole of oxygen. And so if we want to make 0.556 moles of water, that's how much hydrogen and oxygen we need, what we've just calculated there. So then our final step, since we can't weigh out or measure moles, we want to know how much hydrogen and oxygen do we actually need to measure. And we'll learn in chapter 5 that actually weighing gases is pretty hard to do, and there's better ways to do it. But for now, we'll pretend that we can weigh out the hydrogen and the oxygen. And in order to figure that out, we just need to convert to mass. So we multiply by the molar mass of hydrogen. And the same thing with oxygen, we could also just subtract from 10. But let's just make sure it works out here. Okay, moles cancel.
It's 0.278.
Oh, that's right. We used the wrong number here. Thank you. I'm going to say that didn't work out. 0.278. Try that again. Okay, and those should add up to 10, which they do with rounding based on our significant figures. So if these are the masses that we need, if we react 1.12 grams of hydrogen and 8.90 grams of oxygen, we should get 10.0 grams of water, or thereabouts, based on the rounding. Yep.
Can you sketch it down?
Okay, let's see how this works in practice. So grab this sheet here, if you've got it. And let's take a look at this one on the bottom left of the second page. I'm going to copy it over for you. Oops. So we're using sodium fluoride, okay, reacting with this sulfur dichloride to make this other stuff. And what we really want to know is how many grams of this do we need to form 485 grams of this? And that's what the question is asking us. How many grams of sodium fluoride do we need to form 485 grams of sulfur tetrafluoride? So we're going to use that same technique that we just looked at to do this. Anytime we know one mass in a chemical equation, we can figure out any of the other masses by that same strategy. If we think about it as in terms of a conversion, which is really what it is, we're going from grams of SF4 in this case. We've got to first turn it into moles. Then we use our mole ratio from the reaction to get moles of the other thing that we want to turn it into. And finally, grams. So it's always this three-step conversion. Grams of one to moles of that one, moles of that one to moles of the other one, and then moles of the other one to grams of the other one. And you can, in fact, just write it out in one big line as a conversion of one thing to another. So before we do it together, give this one a try and see if you can put it together in that order, just as you did with the conversion problems, and solve for how much sodium fluoride you need. All right, did we get some kind of answer here? Not quite yet? Take a little more time, it's fine. Let me know if you're stuck, but we'll also go through it. All right, keep working if you're still working. I'm going to start going through this one. So I want to set this up kind of all in one big conversion, the way that we've written it here, so you can see how that works. A lot of people find that easier than going step by step. As long as you can do both, you should be fine. So in this case, we're starting with grams of SF4, so that's going to be 485 grams SF4. And then we're going to get rid of our grams of SF4 and get moles. Then moles of one to moles of the other. And finally, moles to grams of the final one. So all the units should cancel appropriately top to bottom each time. Now we need to fill in those amounts. So did anybody get the molar mass of SF4? I'm going to call it out.
108.06.
Okay. 108. And what about NAF? What was that? 41.99. So we'll put that 42.0. And then the middle numbers we get from the equation. That's the mole ratio. So we just use the coefficients directly from the equation. So that's going to be a 4 for NAF and a 1 for SF4. So 4 and 1. Okay. Calculate that through. Okay. That's it. So that's how you do that. It's always the same procedure. So that's the nice thing about this. If you have grams of one thing in the equation, whether it's on the right side or on the left side or whatever, and you want to find grams of another one, you just do this. Always works the same way. All right. Let's look at one where we're not looking for grams, we're looking for moles. It's actually a little bit simpler, but let's see if you can make the adjustment without my specifically telling you how to do that. So we're going to look at the one right above it here. Same type of question. But this time, we're only looking at moles. We're not looking at grams. So think about how you do that conversion in a similar way, but only going from moles of titanium 4 oxide to moles of bromine trifluoride. When you encounter these in a multiple choice format, we'll talk about this, but sometimes you can even do them without calculation. But go ahead and try to do the calculation on this one just for practice. So our plan for this one just looks like one step. We're going from moles of titanium for oxide to moles of bromine trifluoride. Okay. So that conversion is going to look like this: 9.68 moles TiO2, and then we need to convert from moles of TiO2 to moles of BRF3. Our equation tells us 4 of these for every 3 of these. So if we calculate that, we get 12.9, which is this one. So how might we do that without even doing the calculation? Did anybody see a shortcut on that one?
The only number that is higher than 9.68 on there is A, and you know you need like more moles of BRF3 than TiB4. So
Yeah.
Yeah.
Right. So as long as we're given moles, this doesn't work with grams because masses, mass ratios and stuff that we just did before. But if we're given moles, we can say, okay, we've got so many moles of titanium 4 oxide. The equation tells us that they always react in a 3-to-4 ratio. So that means I'm always going to need more moles of bromine trifluoride than of TiO2. And so the only choice there is A, because that's a little bit more. Now, if there were a choice like 12.9 and there were another choice 12.2, then you probably couldn't do that without actually doing the calculation. But the fact that there's only one that's bigger tells you that that's got to be the answer. And thinking in that kind of a way is always helpful because your calculation can go screwy. You can hit the wrong button on your calculator. You can whatever. And if you're thinking, wait a second, what should my number look like? Well, it should be like a little bit bigger than what we started with. That can help you avoid some of those mistakes. All right. So that's how you do these basic conversions, these basic mole calculations. Now let's look at the situations that we call limiting reactants and what happens there.
Are we spending the rest of the day on this?
No.
All right.
We're just going to do this a little bit. And then we'll move to other reactions. So anybody want to explain or describe how you think of the idea of a limiting reactant? What does that mean? Yeah. Yeah. Yeah, so like stuff has to react in a certain ratio, and if you have too much of one, then some of that is going to get left over. It's not going to react. Right? The way that they talk about it in the book, which we might as well go with, it's pizza. So they say that to make a pizza, you need 1 crust. You need 5 ounces tomato sauce, and you need 2 cups of cheese. Sorry, my cheese is green. Didn't have yellow. It's a weird pizza. It's fine. So if you have 1 crust, 5 ounces tomato sauce, and 2 cups of cheese, you can make 1 pizza. I've got my crust, sauce, and cheese. All right. So that's our basic, you can see how that's kind of like a chemical reaction. You have so many of these, have to have so many of these, have to have so many of these. It has to react in that particular ratio. So you might say, all right, what happens if we have 2 crusts, 10 ounces of tomato sauce, and 4 cups of cheese? How many pieces can we make? 2. All right. Now let's say we have something similar. So we have 2 crusts, 10 ounces of tomato sauce, and we drop some cheese on the ground. So we only have 3 cups of cheese. So how many pizzas can we make?
1.
Yeah, you can only make 1 pizza, assuming we don't want to be light on the cheese. And then what would you have left over after that 1 pizza? What?
1 cup of juice.
And what else?
A crust and 5 ounces tomato sauce.
Yeah. So what's stopping you from making that second pizza? The cheese. You don't have enough cheese. So we would call that our limiting factor. If we had another cup of cheese, we could make 2 pizzas, but we don't, so we can only make 1, and then we have extra other stuff. So the cheese is the limiting factor, or if this were a chemical reaction, we call it the limiting reactant. And then the other 2 things we say are in excess. We have more of those than what we need. So the cheese is limiting us from making that second pizza, and the other things are in excess. Okay. So you all kind of just did that in your head and didn't have too much trouble with it. Let's turn that into a chemical reaction, see if you can do the same thing. So let's use a reaction with slightly more complicated numbers here, so that it's not quite as obvious from just looking at it. So we're going to combust some octane, which is the major component of gasoline, C8H18. All right. And let's say that we have two moles of octane and 26 moles of oxygen. So in this case, which one is limiting and which one is in excess? Yeah, the 2 moles of octane is limiting. Why? How do you know? Okay. So if there were, it also depends on how much the other one there is too, right? You're right. But yeah, so the equation tells us that these 2 reactants always have to react in a 2 to 25 ratio. So for every 2 moles of octane, we need 25 moles of water or of oxygen. So if we have more than that amount of oxygen, then we have plenty or an excess amount. But if we have less, that's going to limit how much we can use. So in this case, this one is limiting, and this one is in excess. because there's 26 moles. There's an extra mole of oxygen. What if we had still 2 moles of this? But 24 moles of oxygen. Which one's limiting now? The oxygen, because we need 25 moles of oxygen and we only have 24. So this is now limiting, and this one is now in excess. We have more than we can use of the octane. The important part of this is that the limiting, just like with the pizzas, the limiting reactant is the one that controls how much product you make. So let's say for this one, let's just focus on the carbon dioxide. If we have 2 moles of CH18 and 26 moles of oxygen, the 2 moles of octane is in excess. So if we want to know how much carbon dioxide we make, we have to base that on the 2, not on the 26. In this case, that's simple because that's just the number from the equation. So we would make 16 moles of carbon dioxide. In this case, it's not so simple because we have to base how much product we make on the limiting reactant. So we have to do the exact calculation that we just did when we practiced up here. This question right here. It's the same question, but we have to use our limiting reactant. We always use the limiting reactant in the calculations because that's the amount that we can make. We can't make more than that because we don't have enough. That's the definition of limiting. So we would do our mole ratio here, and we'd say 24 moles of O2 is going to give us how many moles of CO2? Well, there's 16 to 25 per the equation. So we can only make 15.4 moles of CO2. That's the difference between this thing and the pizza example, is we can have fractional moles. So we can actually calculate the fraction of the mole that we would make. Okay, so that's kind of the idea of it, that one of them limits the other one. Let's do some examples and see how this actually works in practice. These are all in grams, aren't they? All right, we'll work through one together. Oops. So we're going to look at this one, this top one on the page here. Potassium chloride, you can buy that as a salt substitute. Calculate the mass of potassium chloride formed when 7 grams of chlorine gas is allowed to react with 5 grams of potassium. Now we're going to talk about how to set up a reaction like this in the second half of today, so I'm just going to do it for you. But chlorine gas is Cl2. Potassium is just potassium, so that's K, potassium metal. And that's going to make potassium chloride solid. We have to balance it. There's a different color here. So there's our equation. And the question tells us that 7 grams of chlorine gas is allowed to react with 5 grams of potassium. And this is the most common way that these types of problems are phrased, and that they don't specifically say find the limiting reactant or which one is limiting. They don't necessarily step you through the process of trying to figure out whether one of the masses limits the other one. But anytime you look at a chemical equation and you're given some masses of reacting, that's something that you need to think about. You need to think, okay, is this a situation where one of them is limiting the other one? Or is this one where everything's even and it doesn't matter? You should always assume that something is limiting unless you're told otherwise. So what that means is that we don't know yet, but one of these is probably limiting the reaction, and one of them is probably in excess, either the chlorine or the potassium. How can we figure out which one's which? So we know they have to react in a 1-to-2 ratio. That's what the balanced equation tells us. How can we figure out which one is limiting here? Can we tell from looking at 7 and 5 and making some distinction about that? Or do we need to do something else? Yeah.
2 grams of, or the 5 grams of potassium.
How do you know?
Because it's got, like, you have more grams of chlorine.
You have more grams of chlorine. But what about the ratio? Where does the ratio come in there?
It's a 1-to-2 ratio.
1-to-2 of what?
Chlorine to potassium.
Of grams?
Oh,
What is it? Anybody? 1-to-2 what? It's moles, yeah. That 1-to-2 is a counting thing. You need one of these for every 2 of these. So not grams. So we can't just look at those masses and say, well, okay, we've got 1 of these and 2 of these. We have to look at the moles. That's the only way to compare that. So you need moles to compare to find the limiting reactant. So those numbers, unless you're very good with estimating things in your head, probably can't lead you to the right answer of what one is limiting. So you need to convert them to moles and compare the moles. So let's do that. So each chlorine is 35.5. So that means Cl2 is going to be 71. It's about 1/10. Okay. And let's look at the other one. So 5 grams of potassium. Each potassium is 39.1. Oops, did both of these wrong. I did this calculation right, but I wrote it wrong. Hold on, let me fix it. Remember, our units need to cancel, so we need grams on the bottom, moles on the top. Sorry about that. All right, so now we've got moles. We're a little closer. How can we figure out whether or not one is limiting or the other is limiting? How can we figure out which one is limiting here? Yeah.
So we need to find the grams for K2K. Yeah.
Yeah, but we can't yet because we can't until we know which one's limiting. So in other words, because they're not in perfect balance, If you start from the Cl2 and calculate KCl, you're going to get a different number from if you start with K and calculate KCl. So we have to figure out which one is right based on which one is the limiting one. So can anybody see which one is the limiting one? Let's calculate it and see. So the equation tells us that we need a 1-to-2 ratio, one of these to two of these. So let's try that and see what we've got. What did I do here? There we go. Let's say if we take that 0.0986 moles of chlorine, let's see how many potassium we would need for that. The equation tells us we need one of these and two of these, 2 potassium. So based on the mole ratio of this equation, if we have 0.0986 moles of chlorine, which we do, we would need 0.197 moles of potassium. So let's compare these two numbers. That's how much we need. That's how much we have. So what we have is less than what we need. What does that tell you about limiting? That it is the limiting. If what you have is less than what you need, that's the definition of limiting. What if this equation had come out opposite? What if we'd come up with 0.05 moles of K or something?
Don't we have to do the other one?
Well, we could just assume then that the other one is limiting, because we'd have more of that one than what we need, so it must be the other one. But you're right, we could also calculate from the other one. So it doesn't matter which one you start with. Let's write this down. We have less K than we need, so that must be the one that is limiting. If you have less than what you need, that's limiting. If you have more than what you need, that's excess. And then the other one is limiting. Okay, so now that we know which one is limiting, we know potassium is the limiting reactant. So we use the potassium numbers to calculate the products. And that looks like this. 0.128 moles of K so we're going to go K to KCl. The equation tells us that's 1-to-1, so 2-to-2. So that means we're going to make 0.128 moles of KCl. And then if we want to convert that to grams, 39.1 plus 35.5, right? 39.1, yeah, plus 35.5 is 74.6, I think. Means that we should form 9.55 grams of KCl. Assuming I did that right. So let's check that. So we're close. It's probably this one. So ultimately, the calculation is the same as what we just did, but we have to find which one to start with by figuring out which reactant is limiting. And the only way we can figure that out is by looking at moles. You cannot figure out limiting reactants just by looking at the masses. You need the moles first. Okay, let's try it again. Do I have another one? I don't have another one on here. Oh yeah, there's some. These all require us to know some more reactions. Let's let me just write down another one for you. We'll get to those other ones after we do the reaction part. Okay, so here's a reaction where we're getting titanium metal from the oxide. So we're taking titanium oxide, reacting with carbon, to form titanium and 2CO. And this is already balanced. Let's say that we're going to react 28.6 grams of this. Oops, no, sorry, other way around. 28.6 grams of this with 88.2 grams of this. How much titanium can be produced? Try to work on this one together. So work in your groups with the people you're sitting around, or move your chairs around if you want to work with other people. And see if you can walk through this. Let me remind you of the steps of what we did before. So we're given two masses, but we're not sure whether those masses are actually stoichiometric, meaning that they're in balance, or whether it's a limiting excess situation. Since this is what we're practicing, I'm going to assume it's probably a limiting reactant situation. So that means you need to convert those numbers to moles, compare based on the mole ratio, and figure out which one's in excess and which one is limited. Once you figured out that, then you can use the limiting one to figure out how much product you make. Give that a try. Let me know if you're stuck.
Get by changing the gram to moles, correct?
Right.
And then by turning it into, or remember it.
All right, yeah. Yeah, so you're going to convert one from grams, convert both from grams to moles.
Yeah, I did. And then I
Then use the mole ratio to go from moles of one to moles of the other. That tells you how much you need. And
So-
compare what you need to what
so
you're at.
if you like say take the carbon
Mhm.
and you turn that into the mole ratio turn into titanium oxide.
Yep.
Okay.
And then see how that compares to what you got.
Okay.
No, you only do that when it's a substrate right at the front.
Yeah, I'm doing math, it's like, so, yeah, I'm gonna end up with needles that you create. If I have, and I get more than the dioxide, oxide. But if I do the same thing with the oxide, I'd say I need more carbon than I have, so.
Right.
It's like both 4%.
Yeah, you're thinking about it. So you convert, if you get a larger number for the titanium oxide that you have.
Yeah.
And then you also get a larger number of the carbon that you have.
I get a smaller number.
Okay, so you get a smaller number, that means that you're in excess.
Okay. Yeah.
If you write it down and like compare the numbers, there's less chance of getting to down. Yeah. Yes, you don't know which one you're using. So you have to, yes, do the ratio between these two. More or less. That would be like one of these. The second one would be this. I create another one. Yeah. Yeah. Yeah, you the molar mass is only calculated based on the substrate, so you basically formula it, so you don't use the correlation. Grams of TI, yeah, once you figure out how much. No, because well, in this case, yeah, because they're 1-to-1 ratio, so it's just 1-to-1. Because of the equation. All right, so what did you find was limiting in this one? The TiO2?
Yeah.
All right, let's see if that works out. So you convert these to moles, right? What's the molar mass of TiO2? What? 79 point. That's fine. So you get 1.10 moles. And then we do the same thing for carbon. We got 2.38 moles of carbon. So now it doesn't matter which one you start with, but you're going to try to use the mole ratio to figure out how much of the other you need. Since we did TiO2 first, we might as well just start with that one. So we're going to take 1.10 moles TiO2, and then we're going to go from moles of TiO2 to moles of C, using the ratios in the equation, which are 2C to 1 TiO2. So this tells us that for 1.10 moles of TiO2, we need 2.20 moles of C. So now we're going to compare these two. And what does that comparison tell you? We have more than we need, or we need more than we have? We have more than we need. So the bottom equation tells us that we need 2.2 moles of C. We have 2.38. So that means we have more than we need. And so that tells us that carbon is in excess and TiO2 is limiting. That means we're going to use the TiO2 for the rest of the calculation. So this time we want to go from TiO2 to Ti, because that's what the original question was asking. I think that's 1-to-1 in this equation. Yep. So then we can put in that molar mass too to get our final grams of Ti. So it's 47.9. So we should end up with 52.7 grams of titanium. Is that what you got? Okay. Last thing we're going to talk about before the break, and then we'll come back and talk about solutions and reactions. Is this idea of yield. Have you heard the term theoretical yield? What we've been calculating is exactly that. So this 52.7 number that we got, like how much titanium do we expect to make from a certain number of these reactants? That's called the theoretical yield. Yield just means like how much you get. It's theoretical because you can never in a chemical reaction perfectly convert all of the starting materials to products. There's always just thermodynamic things going on. There's equilibrium issues going on. There's it's not like mistakes or error. It's just that's how chemical reactions work. You can't convert them 100% into the products usually. So the theoretical yield isn't actually attainable. I mean, you even noticed this yesterday. Like if you're doing some sort of procedure, there's no way to get literally every single atom of your product onto that filter paper. There's always going to be something that kind of sneaks through or goes around or whatever. So the yield that you would expect is a theoretical yield. It's not an actual yield. So we can distinguish our theoretical yield from our actual yield. So the actual yield is what you get. The theoretical yield is, well, let's rewrite that a little bit. Theoretical yield is the most you could possibly get. Which, if you actually got that much, probably means something went wrong. If you get more than your theoretical yield when you do a reaction, something's definitely wrong. Maybe it's wet, or there's extra mass in there from something, some impurity. You can't get more than your theoretical yield, because that's the most that you could possibly get. So then we can define this ratio that's quite useful, the percent yield. It's just a percentage of the theoretical yield. So let's say let's say we actually did that previous reaction. I'll leave that there so you can write it. We actually did that previous reaction, and instead of getting whatever we got, I do have to move it up now, sorry, 52.7 grams. Let's say in the above reaction, we got 46.2 grams at the end. So then our percent yield is 46.2 grams over 52.7, converted into a percent, 87.7%. That's our percent yield. That's an important number. That's something that you would report anytime you did some kind of a reaction in any situation, even in like an engineering and a non-chemistry situation. You would want to know, as we do this reaction, what is our percent yield? So if you read like a chemistry paper where they do some reaction and they report their percent yield is 87.7%, then you know when you do the reaction, you can compensate for that. So if we need 10 grams of product, but it only gives us an 87.7% yield, then we know we need to use a certain amount more, an extra 13% or whatever it is, to compensate for that loss. So we can still get back as much as we need. So the percent yield is an important calculation when we do chemical reactions. The theoretical yield we've already calculated. That's often what this calculation is used for. How much of the product can you make based on how much you started with? And that's our theoretical yield. All right, that was a lot of stuff. Any questions about that? All right, let's take a break now. We'll come back. We'll talk about solution chemistry and reactions, and then we'll hopefully have plenty of time to practice all this stuff before we go.
Is solution chemistry like going through all those different kinds of like 6 kinds of reactions or something?
Yes.
All right.
Yep. Yeah, we'll see. It's a lot because we got to do oxidation reduction. So the last thing that we can use in these types of calculations is solution chemistry, solution stoichiometry. So anyone know what a solution is? Everybody know what a solution is, I'm hoping?
Just a mixture of, it needs to be a mixture of things in water.
Yeah, it's just another name for a homogeneous mixture. So it could be in water, but it could be solids, it could be gases, whatever. The ones we're talking about now are going to be water solutions. What's the concentration unit that we most use in chemistry when we talk about water solutions? Anybody know?
Molarity.
Yeah, molarity. We'll get more into like the details of solution chemistry in chapter 13. I'm not even sure we'll get there this semester. That's probably going to be next semester. But so we're not going to get into like all the little details of solutions and intermolecular forces and all this stuff. But we should talk about a few things that will affect what we need to do. So for that, mainly we want to know how much of whatever is dissolved in water is actually dissolved in water. So we use a quantity called molarity for that, which is defined as moles of solute per liter of solution. And there are other ways of measuring solution concentration. There's mass percent, volume percent, mass by volume, molality. We may get into those later depending on our timing. But for now, this is what we need, because this is going to tell us how much of whatever you were using is in the solution. So like yesterday in lab, we used a 6 molar solution of nitric acid. A 6 molar solution of nitric acid means that there are 6 moles of HNO3 per every 1 liter of solution. So that means that if we had, let's say, 5 milliliters of nitric acid, that's 0.005 liters, or I'm sorry, 5 milliliters of 6 molar nitric acid. That would be 5 milliliters times 6 moles per liter. So by using molarity, we can figure out exactly how many moles are in a given amount of solvent. And that's really important for the types of reactions we've just been doing, because we need to be able to calculate how much of something we need or how much we're going to make. So if that something is in solution, we're going to use molarity to do that. The nice thing about that is we don't have to do any grams conversions in this case. We can just stick with using the molarity. So by multiplying by the volume, we can figure out how many moles that is. All right, let me show you how this works and how this gets incorporated into the types of calculations we've just been doing. What's that thing again? Oh, there it is. Okay. So I'm going to look at this very last one here. I'm going to get a little more room. Hold on. So a problem like this. So we've got, this is basically the same kind of problem that we did before. We're given a certain amount of reactant, in this case, NaHCO3. We've got 23.2 grams. And we're asked, how much HCl do we need? But because HCl is a solution, we need that number in milliliters of a particular concentration solution. So let's see how we figure that out. So the beginning of this type of a problem starts just like the other ones. We convert grams to moles and figure out how many moles we have. So 23.2 grams of NaHCO3. We're going to go from grams to moles. We're given the molar mass here, so that's 84.02 grams per 1 mole. So we're starting with 0.276 moles of NaHCO3. So just as we did before, we need to know how many moles of HCl are needed. So how do we figure out how many moles of HCl are needed now that we have moles of sodium bicarbonate? How do we figure out the number of moles of HCl needed? Yeah.
You could then do the molarity, so you could say like 1.58 moles, like you can change the two from,
Well, hold on, we're not quite there yet. We just want to know how many moles of HCl do we need?
like you can change from moles, you can do the mole ratio.
Yeah, we're going to use the mole ratio from the reaction.
Yeah,
Excuse me, thank you. So what is the mole ratio between sodium bicarbonate and HCl in the reaction? 1 to 1, right? Because the equation just has coefficients of 1. That is a balanced equation. So that means we also need 0.276 moles of HCl. So now the question is, what's the volume that we need? In order to find the volume, we know what the concentration is, and we can set up a proportion to figure that out. So we can say 1.58 molar solution is 1.58 moles of HCl per 1 liter of solution, right? That's what that means by definition. That's what molarity is. Since the concentration has to stay the same, we can set up that proportion to say, okay, well then we know we want 0.276 moles of HCl. So how many liters is that going to be? We solve that proportion by cross-multiplying and dividing or rearranging or however you've learned to do proportions, and you end up with 0.276 divided by 1.58, which is 0.175 liters or 175 milliliters. So think about the steps there as we've done that. We figured out how many moles we were given, how many moles of the other thing we need, and then rather than figure out what that would be in grams, we figure out what that would be in milliliters of a particular concentration solution. So that's the difference when we use molarity. That's how that changes. Other important things about solutions before we get into solubility and reactions. One thing would be dilution, solution dilution. The official equation of dilutions that you've probably seen before, C1V1 equals C1V2 or C2V2 or M1V1 equals M2V2. C is for concentration. Volume. And it's really just saying those two things are proportional. So if you have a certain concentration times a certain volume is actually, if we think of concentration as molarity, concentration times volume is moles. So moles are always the same. Moles of solute are always the same regardless of how much water you add. That's why this works. Because you add more water, you still have the same number of moles. The volume changes, the concentration changes, but the number of moles are the same. So for example, let's say we have, that's not a good example. All right, so let's say we want 525 milliliters of a 1.20 molar sodium chloride solution. That's like what's happening up here. So say you're doing a reaction, you need a certain volume of a certain concentration of solution. How should we make it? From a 6 molar stock solution. So this is how you would typically do this sort of thing. You do your stoichiometry calculations, you figure out you need 525 milliliters of a 1.2 molar solution. Okay, great. It's 1.2 molar, that's not like a standard concentration, but we've got a bunch of 6 molar solution ready to go. So how do we make the 1.2 molar out of the 6 molar? Use the equation from above. So we're going to start with 6 molar, that's our C1. And our V1 is what we're solving for. How much volume of that 6 molar solution do we need to make ultimately a 1.2 molar solution and 525 milliliters of it? Because you got the same thing on both sides, you don't have to worry about converting units as long as you got the same units on both sides, because they'll end up canceling each other anyway. All right, so you'd solve this for V1 using your algebra skills. So 1.2 times 525 divided by 6. And so that tells us we need 105 milliliters. So how we would make this is we would take 105 milliliters of our 6 molar solution, add it to whatever container, and dilute it so that the solution ends up at 525 milliliters. And then we can use that for whatever we're doing. So you see how that works? So you just solve. If the questions were the other way, same exact equation, you're just solving for the other side. So another way we could do it would say like, well, let's say there's one in the book here that says, to what volume should you dilute 0.2 liters of a 15 molar solution? So if they're saying, what volume should you dilute it to? That's talking about V2, the second volume. What are you going to? What are you going to make? So just read the question and see what you have and what you need to make. This will come up in lab in a few weeks. As long as you remember that equation or some variant of it, you should be fine. Even if you forget the equation, you can do it by moles. You can just convert to moles and do it that way. But it's a lot easier if you just use this equation. All right. So that's all the calculation stuff for now. Let's talk about aqueous reactions. So I'm going to put up a picture here. If I can find it. Yep, this one. Do not need it that big. So here's a neat picture about how an ionic compound dissolves in water. You probably have an idea of what this means, but it's neat to see it visually. So you've got this chunk of, let's say, sodium chloride, and as it goes into water, the water molecules kind of tear off molecule by molecule and surround them. And so even though these are shown as circles here, they're really spheres. They're going all around. They're encircling the ion completely. So in order for something to dissolve in water, there are two competing forces, two competing chemical forces here. There's what's called the lattice energy, which is the force holding those ions to each other. And then there's the force of, or the energy of solution, which is the energy that's gained by the water molecules all surrounding it. So if the lattice energy is super, super strong, and the ions don't really like being surrounded by water, then there isn't a great energetic incentive for those water molecules to tear off those particles. And so the thing's going to stay together and it's not going to dissolve in water. That's why, so you probably heard before in previous classes, things like dissolves like charged polar things dissolve in polar solvents, that kind of thing. That's sort of true, but there are plenty of ionic compounds that don't dissolve in water. And it's not because they're not charged, it's because of this competing interaction, that they'd rather stay together as a lattice than get broken apart into water. And so one of the things we're going to be looking at in this chapter is how can you determine whether or not something's going to break apart, something's going to become an electrolyte. Unfortunately, there's not like an easy concept to remember that just always gives you the answer here. So we have to do a little memorization. So I will put this in here. Hopefully you've seen something like this before, but it's probably still going to take a little bit of work on your part. So in order to determine whether or not something will be soluble in water, we follow rules like this. You can actually look up these solubility values, but nicely the book has kind of summarized them for us. And the only thing that's kind of nice about this, really, is that at least they fall into some general rules. So even though there's a lot of ions to think about, there are some general rules that can get us in the right direction. And even if you don't memorize every last one and every single exception, you're probably going to get 90-some% of them right just by remembering a few simple rules. So I'm going to highlight the simple rules that you should remember. Those are, this one's really important. All the salts of the alkali metals, most of the alkali metals, and ammonium are always soluble in water. So any lithium, sodium, potassium salt is always soluble in water. Nitrates and acetates, always soluble in water. So just by remembering those two, you've covered a lot of possible situations because you usually are going to make at least one alkali metal salt and maybe a nitrate salt as well. Okay. And we're actually going to ignore the rest of this for now. We're going to come back to it as needed based on what we're about to do. So if you can just remember those things right now, the alkali metals and ammonium, nitrate and acetate, soluble, always soluble in water. It will always dissolve in water. The way we're going to use these right now is by looking at precipitation reactions. The goal of this chapter, by the way, what we're going to be doing for the next hour or so, is so not only can you write down reactions that you're given based on what we did last week, but now you can actually predict the products of reactions. So if I just say, here's this chemical and this chemical, what happens when they go together? As long as I give you certain ones, you should be able to at least make a good guess at what that answer is going to be, what they're going to make. One large class of reactions that we're going to look at is the precipitation reactions. So those look like this. We're going to do some tomorrow in lab. I'm not going to copy this one in, but so you pour 2 clear solutions together. We're going to do this a bunch tomorrow. And you make this kind of cloudy solid. Sometimes it's really striking and obvious, like this yellow lead iodide precipitate. Sometimes it just kind of makes it cloudy. Remember yesterday, you made a precipitate in your lab. That was the white stuff that fell to the bottom. It was also the stuff that made it cloudy in that second part, in that part B. That's an example of a precipitation reaction. So what's happening is you're taking 2 soluble salts, mixing them together, and you're making something that's insoluble in water. Because it's insoluble in water, it becomes opaque. And so you get from a clear or translucent solution to an opaque solution that you can't see through. Sometimes you see actual particles. Sometimes it just looks cloudy. But that cloudiness is evidence of a precipitate, of something insoluble forming. So here's one of them. Here's one reaction: potassium iodide and lead nitrate. Those are all soluble. So why are those 2? How would you know, based on what we just talked about, that those 2 reactants are soluble? Which rules do they follow? Yeah.
Potassium first reactant.
Yeah.
Nitrate.
Yeah, potassium in the first reactant, nitrate in the second reactant. So you know they've got to be soluble. Now look at the products. If you had to pick one of those products to be soluble, if you weren't told, all you know is one of them's soluble, one of them's a precipitate. How would you pick which one? How would you pick which one is soluble? How would you know that the one on the right is soluble? Yeah, it follows both rules. It has a nitrate and it's a soluble in alkali metal. Okay, so even if we didn't know the rules about lead and iodide and all that stuff, we could at least make a pretty good guess that the other one is soluble, because it definitely has potassium and nitrate. All right, so let's try another one. Hang on, sorry, I lost my place here. Okay. Potassium carbonate and nickel 2 chloride. So we're going to react these 2 and figure out what the products are and figure out whether or not there's a precipitate formed. So how do you figure out what the products are in a reaction like this? Yes. What? Yeah, you switch places. So this is called a double displacement reaction, and you switch ions. I think it's actually most helpful if we do it by the names instead of by the formulas, so we don't get distracted by the subscripts. So we would call this one potassium carbonate. And we call this one nickel 2 chloride. So then our products are going to be trading places with cations and anions. So the nickel 2 is going to go with the carbonate. And the potassium is going to go with the chloride. So now we can write the products. And if we write the names first, then we can construct the appropriate formulas. So we're first going to put the nickel 2 with the carbonate. That's going to be one product. Then the other product is going to be the potassium with the chloride. The reason I did it by names first is because it's not as simple as just switching them with their subscripts. We have to figure out new subscripts for the new compounds. So we can't just take that K2 and put it with the Cl2. We have to reconfigure that. So let's start with potassium chloride. That's easier. We know potassium has a charge of what? plus 1, and chloride? Minus 1. So what's that formula? KCl. Okay. And then what about nickel carbonate? So nickel 2 we know is nickel 2 plus, because we're told it's 2. What's carbonate? Yeah, CO3 minus 2. So what's the formula of nickel carbonate? Yep, just NiCO3. All right, so that's our full equation. Now we're almost done. We've got to balance it. So that means we just need a 2 over here. And then we need to put in the phases. So of those two products, are any of them, do we know that any of them are for sure soluble? KCl's got to be soluble because all potassium salts are soluble. So we can put an AQ there because we know that's soluble. Now what about nickel carbonate? Yeah, we could probably, now we have to go back and consult the chart. But if we're just going to guess based on those couple of rules I told you to remember, that's probably going to be insoluble, right?
Also, the fact that precipitation reactions, something has to be a solid.
Right, right. So I kind of gave you a clue there. So something has to be a solid. We can be pretty sure it's that just based on those two rules that we already remember. But if we really want to be sure, let's go back to the rules and look at carbonates. And it says here, carbonates are generally insoluble except when they're with those ones from the top. So when carbonates and phosphates are with those alkali metals and ammonium, they're soluble. Otherwise, they're always insoluble. So that tells us that, yes, this one is definitely a solid precipitate. And that tells us that this reaction actually happens. It goes forward. All right. So let's think about what's actually happening in solution. In an actual solution, those reactants are not together. We just talked about that, how they're split apart. If you have a soluble ionic salt, then the ions are split apart in water. So often, or sometimes, what we write to express that is something called the complete ionic equation. The complete ionic equation is when we break all of the ionic solids up into their constituent ions. And this gives us a better picture of what it really looks like in solution. So we don't just have K2CO3. What we really have is 2 potassium ions in solution and a carbonate ion in solution. Remember that picture? So the ions are actually separate and surrounded by water molecules. And then we don't really have nickel chloride together. We have a nickel 2 plus ion that's surrounded by water. And we have 2 chloride ions. So notice how I move that subscript out in front as a coefficient, because in solution, those ions would be separate. They wouldn't be together in a compound. They would be separately floating around in the solution. And then on the product side, we would keep the nickel carbonate together because that is together in a compound. It's a solid, it's insoluble, which means it's not broken apart into ions, it's together as a solid. So that actually stays together. We don't break the solids apart. Same thing with gases, same thing with pure liquids. Anything that's not an ionic compound doesn't get broken apart in a complete ionic equation. But the potassium and the chloride would be, because those are dissolved. So there's our complete ionic equation, where we've expressed all of the ions in solution. And this kind of illuminates something else interesting that's going on here. which is that the potassium and the chloride are the same on both sides of the equation. What does that mean, that they're the same on both sides of the equation? What happens when there's two of the same thing on each side of the equation? Yeah, they kind of cancel out. It means nothing's happening to them. Nothing's changing. They're staying the same. They're not really participating in the reaction. They're just still there. So these ions are not participating in the reaction, and we call those spectator ions. So the only reaction that's really happening in the solution is nickel and carbonate are coming together to make nickel carbonate precipitate. Nickel 2 carbonate precipitate. And so that gives us our second way of writing, or our third way of writing an aqueous equation, which is called the net ionic equation. Which is only showing the change, the thing that's actually happening in the solution. So in the net ionic equation, you don't show those spectator ions that are just floating around, and you only show what's really happening in the solution. So in that case, this would look like CO3 2 minus plus nickel 2 gives us solid nickel carbonate. All right. So this can also help us to understand when there's no reaction, because that's not always clear when we're just writing the regular aqueous reaction like up here. But for example, right, the molecular equation, which is the kind of the first one, the basic one. For the reaction between potassium iodide and sodium chloride. So see if you can put those together. I give you two reactants. You're going to write them, draw the molecular equation based on, or write the molecular equation based on constructing the products by switching ions, and then write the complete ionic and net ionic equation. And something weird is going to happen. See if you can figure it out. Yep. What? So there's what? Right. Yeah. Maybe I'm having trouble there for a second. This is what you got for your molecular equation. You just switch parts. Everything's a plus or minus 1 ion here. So is this a precipitation reaction? Why not? Yeah, because there's no insoluble product. You've got NaI, which Na is a alkali metal, so it's going to have a soluble. It's going to be a soluble salt. And then you've got KCl, which is also soluble. So you've got 2 soluble products, so no precipitate. So that's kind of a problem. If we write the complete ionic equation, we can kind of see why that's a problem. All of these are going to get split up in solution. And I can actually copy this entire list of stuff and put it over on the other side too, because it's all the same. So that means that they're all spectator ions. They all cancel. And there's actually no net ionic equation. Since the net ionic equation shows change, if there's no net ionic equation, that means there's no change, which means the appropriate way to write this would be to simply say that this is no reaction. So sometimes you'll see this in the homework. It'll say something like, write the products of this reaction. If there is no reaction, just write no reaction.
So the only time that you include like the right-hand side of the molecular formula, the formulas, if there's a percentage.
Not quite, because there's other types of reactions too. So the better way to phrase that is only when the net ionic equation exists, when there is some change shown. We're going to go through a couple other types when we also see that. So it's not just precipitation reactions, but if there is nothing that changes, then it's no reaction. So So that's one way that we can use those solubility rules to determine that. All right. So before we go into the other three types of reactions that can show change, let's look at a couple examples and just to practice this a little bit. So I'm going to give you a couple reactions. I want you to write them out and then decide either write the products or write no reaction if there's no reaction. So first we've got chromium 3 nitrate. Reacts with lithium hydroxide. And these are both aqueous. You can assume these are aqueous. And then ammonium chloride reacts with calcium hydroxide. So write the molecular equation, the balanced molecular equation. If there's no reaction, write no reaction. All right, so here's what these reactions look like. Again, first you're gonna put the compounds together and then switch partners and see what they end up looking like on the other side. So chromium 3 nitrate is gonna be CrNO3 3. And you can assume that whatever you start with is gonna be aqueous unless it's specified that it's a gas or something, or a solid. And that's gonna react with lithium hydroxide, LiOH. When those switch, that means we've got CrOH3 and LiNO3. So looking at the phases on the right, would you expect any of those to be soluble for sure?
LiNO3.
Yeah, the lithium nitrate definitely follows that rule. What about the chromium hydroxide? You might guess. What would you guess? If you had to guess, what would you guess?
Insoluble.
Probably insoluble. Just, I don't know, because it's not one of those other ones, so you might as well guess it. If we want to be sure, we want to look at the table. And if you really want to always get this right, you can memorize the table. But you can also, be pretty good with guessing this as long as you know some of the general rules. So in this case, hydroxides are usually insoluble, but there are several exceptions. We don't have one of them here, so it is definitely insoluble. So we can put an S there. So that's definitely going to occur, right? It's not balanced right now, so we've got to balance it. But that reaction will happen. It will form that precipitate. So then we've got ammonium chloride and calcium hydroxide, NH4Cl. So then we're going to get ammonium hydroxide and calcium chloride. And what about these two? Soluble, not soluble?
First one, a soluble, second one not.
First one's soluble. The second one, actually, table here, whoops. Chlorides are generally soluble, with a couple exceptions, silver, mercury, and lead. So halides are usually soluble. So in this case, they're both soluble. So once you've determined that both of the products are soluble, you can just kind of say that this is no reaction.
When you say no reaction, does that mean that it would never turn to that side, or what?
That's right, because when you think about it from a net ionic standpoint, the two sides are the same. So by mixing those two things together, you're not actually doing any chemistry. You're not changing anything. Right.
They're just all the three.
It's a physical change. You're physically mixing them together, but you're not chemically changing anything.
Okay.
Yeah. So that's why we say no reaction. That can be better thought of as a mixture than a reaction. Yep. All right. So the best way to do to get used to these is not to, pour over your tables and your notes and try to study everything. Is to practice. Just do them over and over again. Try a bunch of these. The Mastering Chemistry for Chapter 4 is a little different in that it's a bit longer and the follow-up is very short. So the goal is that you spend a little bit more time with the homework. As usual, it is due the week kind of after we're talking about it so that you have plenty of time to do it. But it will be on the exam on Monday, so please get working on that.
So no lab on Monday, but exam?
Right.
Okay.
Okay, so and if you want, let's see, speaking of that, so normally labs are always due the week after we do them. So Monday's lab would be due on Monday, but since that's an exam day, let's just make that due on Wednesday also. So all the labs from this week will be due on Wednesday. That said, these labs this week are also good practice for the exam. So you should do the calculations and stuff beforehand, but they won't be due. All right, let's look at the last couple parts of Chapter 4, and then we will have a little time to practice before the end. I'm just going to start a new page. So we spent a lot of time talking about precipitation reactions. You should also be able to recognize a couple other special kinds of reactions. We're going to look at gas evolution reactions, reactions that form gas. Acid-base. We're just going to talk a little bit about identifying an acid-base reaction and drawing the products. Later in the semester, and actually next semester, you'll talk way more about acids and bases. And then oxidation and reduction. So these are the other aqueous situations where the net ionic equation exists, where it's not blank. Let's look at that first one. Gas evolution reactions are things like this. So if we imagine a like a double displacement type reaction between HCl and sodium bicarbonate. So we've got hydrochloric acid, but we can think of that as H plus and Cl minus, and NaHCO3. If we switch partners like we normally would with a aqueous double displacement reaction, we would get NaCl and carbonic acid. So it almost looks like there would be no reaction at all because of that. But what happens is carbonic acid isn't a stable molecule in aqueous solution. So what happens is this spontaneously and immediately becomes water and carbon dioxide. So carbonic acid decomposes into water and carbon dioxide, and so of course NaCl is still there too. But that is the gas, and of course if you do this reaction you'll see bubbles. That's like the famous volcano experiment, except with HCl instead of acetic acid. Sodium bicarbonate is baking soda, so you put those stuff together and you see bubbles. So if you see bubbles, you've got a gas evolution reaction. If we think about the net ionic equation here, you've got H and Cl, which break apart into H plus and Cl minus, and then Na and HCO3, and then the product becomes what it becomes. So let's write this out. Complete ionic equation. We're going to have aqueous hydrogen and chloride, sodium, and bicarbonate on the left. And then on the right, we have to skip that middle part, because remember, this isn't actually something that we isolate. That just is the middle, that's just the intermediate. What we actually see is the product. So now we've got sodium ions, chloride ions, water, which stays together as a liquid, and CO2, which stays together and actually leaves the solution as a gas. So if we get rid of our spectator ions, then our complete ionic equation is H plus and H, or our net ionic equation is H plus HCO3 minus yields H2O and CO2. So the big question about this, or the hard part about this, is how do you know? If you're just given two reactants, how do you know that they're ultimately going to produce a gas? How do you know that this is not just going to be carbonic acid? So the trick here is to look for a particular type of reactants. So we're going to look for sulfides, carbonates, and bicarbonates. So CO3, HCO3. Sulfites and bisulfites. I guess we'll stick with words here. Hold on. So those are SO3s. Carbonates and bicarbonates, CO3 2 minus, and HCO3 minus. Sulfites and bisulfites, SO3 2 minus, HSO3 minus. And ammonium can also do it. So what you want to look for in each of these is the types of products that we know are somewhat unstable and end up evolving gas. And there's a neat table in your book, so I'll put that here, that summarizes all of that very nicely. It kind of shows you what to look for. So when you see sulfides, for instance, reacting with hydrogen, you form H2S, which is a gas, hydrogen sulfide. So there's your gas evolution. With carbonates and bicarbonates, there's an intermediate product of carbonic acid, but we don't really see that. So anytime you see carbonates or bicarbonates reacting with acid of any kind, you're going to form carbon dioxide. Same thing with sulfites and bisulfites. If they're reacting with acid, they're going to form SO2 instead of CO2. And then ammonium, when you form ammonium hydroxide by reacting with hydroxides, that will actually decompose into ammonia gas. So those are the examples of compounds that undergo gas evolution. Again, as you practice this in lab tomorrow, there's going to be a lot of equations to write, and you'll see this. Okay. So then we've got acid and bases. What do we look for there? You want to? Yeah. Salts formed is one. Water formed is another one. But what if we're trying to predict the reaction? Like what kind of reactants are we looking for? Yeah, we talked about acids, right? We talked about how to name acids by things that start with H. So that's what you're looking for. When you see those acids and you see them reacting with certain types of other things, which we'll look at right now, hydroxides mainly, then we know that we can call that an acid-base reaction. So let's look at kind of a classic one. We're not going to get all into the acid-base chemistry now. Like I said, we'll do that another time. But if you have HCl, which we know is hydrochloric acid, because we know that name, that should be your first clue. Okay, something's going on here. If you're reacting with an acid, it's not just a regular double displacement precipitation reaction. It's either an acid-base reaction or a gas evolution reaction or something else weird. But we got hydrochloric acid, and we're reacting with a hydroxide, sodium hydroxide. If you think about switching partners, the double displacement here, the H goes with OH. Well, H and OH make water. So if you've made water, that is now a pure liquid, which will give us a net ionic equation. So the net ionic equation for an acid-base reaction is always H plus, for the ones we're going to see anyway, H plus OH minus gives H2O. If that's the kind of net ionic equation that you're getting, or that's what's happening when you're switching partners, you're getting HOH, you're getting water, that's your clue that you've got an acid-base reaction happening. So the big key here is forming water. The formation of water tells you that it's an acid-base reaction. All right. So gas evolution reactions, acid-base reactions, precipitation reactions. Good on that so far? I know it's a lot of stuff today. It's going to take some practice. Let's look at the very last bit, which is oxidation and reduction reactions. We often just shorten this to redox. So oxidation reduction reactions involve transfer of electrons from one reactant to another. Which it seems like we're always transferring electrons around, but the reactions that we've seen so far, nothing's changing its charge. Nothing's changing how many electrons it has. You just have different pieces kind of coming apart and then coming together. In this class of reactions, we're actually changing where the electrons are. They're going from one reactant to another. So let me show you an example of that. Sodium solid reacts with chlorine gas to make sodium chloride salt. How do we know that this is a redox reaction? Well, things have changed their oxidation state. Now, oxidation state isn't the same thing as charge, but for ions it is. So we know in sodium chloride, what's the charge on sodium? Yeah, sodium's +1, and what's chlorine? -1. What's the charge on sodium when it's just sodium metal by itself? Yeah. 0. Yeah, any element all by itself has an oxidation state or a charge of 0. So for chlorine in the Cl2 molecule, that would also be the case. That chlorine in its elemental state in Cl2 has a charge or an oxidation state of 0. So we can see in this reaction that we've transferred electrons from the sodium to the chlorine, because sodium has gone from 0 to +1, and chlorine has gone from 0 to -1. Let's write that down. Sodium in this reaction goes from sodium 0 to sodium +1. So that means that it has lost 1 electron. Chlorine has gone from Cl0 to Cl-, which means that it has gained 1 electron. If you lose an electron, that's called oxidation. And if you gain an electron, that's called reduction. So we would say that the sodium has been reduced and the chlorine has been, or I'm sorry, the sodium has been oxidized and the chlorine has been reduced. There are various ways people remember this. One simple one is just reduced means to go down in number. So if you're +1 and you go to 0, if you're 0, you go to -1, -1, -2, -2, -3. That's going down, so that's reduction. I don't know, anybody else have any ways that you like to remember that? Yeah. That's another good one. Yeah, loss of electrons is oxidation, so that's Leo, and then gain of electrons is reduction, that's Ger.
Oil rig.
What?
Oil rig.
Oil rig, that's another one. How's that work? Oxidation is loss, reduction is gain, oil rig. So however you want to keep that straight is good. The really tricky part about this is how do we know whether things are losing electrons or not if it's not simple like starting with elemental things like this. So we actually have rules for assigning oxidation states because, let me give you another example. Well, here's a good way to think about it because I think this is always true. Since elements in their elemental state are always zero, if you have some elements that are pure elements like sodium and chlorine, and then they come together and form a compound, there has to be oxidation reduction involved there. Same thing if it's the opposite. If you've got a compound and then it's broken down into individual elements by the pure elements, that also has to be redox because you have to have gone from something to zero. Elements don't have zero oxidation states in compounds. So that said, let's look at another simple reaction that we've looked at before. So is this a redox reaction or not? Based on the rule we just wrote down, is it or not?
Yes.
It is. It has to be because you've got individual elements becoming a compound. So H2 must have a charge or an oxidation state of 0, O2 oxidation state of 0. But what are the oxidation states of H and O and H2O? Is that an ionic compound?
No.
It's not. So how do we assign oxidation states if we don't have charges? And that gets a little bit tricky. So that's what we're going to look at now. There's some rules for doing this. First, the oxidation state of an atom in a free element, that's what we just talked about, is 0. So whether you've got H2 or O2 or just copper metal or aluminum metal or something like that, it's always 0 oxidation state. If it's not a compound, if it's just one element, it's 0. Second, the oxidation state of a monoatomic ion is equal to its charge. So remember I said oxidation states aren't quite the same thing as charges because even non-charged atoms and compounds have oxidation states. It's more of a way of electron accounting, keeping track of where the electrons are. So if you have NaCl, sodium's oxidation state is +1, just like the ion in NaCl is +1. So 3, metals always have positive oxidation states. In compounds, of course, because otherwise they're 0. So a metal will never have a negative oxidation state in a compound. And then we're going to assign others by this chart. I'm going to copy this over from the book. That's a really big chart. So that's better. Okay. So what this means, this is actually in order. And we've got about 15 minutes so we can practice this. So it goes 1, 2. And it's telling you what is most likely and what takes priority over others. So that says that if you have a compound with hydrogen and oxygen in it, like water, you're going to first assign the hydrogen to +1 because that's higher up on the list. And then you're going to assign the oxygen. And what that's telling us is that there's a better chance that hydrogen is going to be +1 than oxygen is going to be something other than that oxygen is going to be -2. So let's look at some examples of some compounds. First of all, let's write that down. Water. So using the chart, we first assign that H has an oxidation state of +1. And then we go down the list and we find oxygen, and we assign that to -2. Okay. So let's take a look at some. Sorry, one more rule. Oxidation states of all atoms in a compound must add up to the overall charge of that compound. So let's look at where this kind of gets sometimes tricky. Cr2O7. Okay. Actually, that's an ion, right? And what's the charge on dichromate ion? Yeah, that one's -2 overall. So what that's telling us is that in this compound, chromium and oxygen are going to have certain oxidation states. And those oxidation states need to add up to -2. So we go to the chart and we say, okay, which do we assign first? So which do we assign first here? Chromium or oxygen? Oxygen. Chromium's not even on the chart because metals get all crazy. So just oxygen. We know oxygen has to be -2 from the chart. There are 7 oxygens, which means we have -14 total, right? So the chromium oxidation state must be what? Close. What does it have to add to overall? -2. So what plus 14 is -2? Yeah, so we need total 12, so chromium must be +6. 2 times +6 plus, -14 equals -2, the overall charge of dichromate. So in dichromate, chromium has a +6 charge. There's another one. Two of them. CO2 and CO. So carbon dioxide and carbon monoxide. Those are covalent molecular compounds. They don't have charges, but they still have oxidation states. So how do we assign the oxidation states in CO2? Which one do we assign first? Oxygen, because oxygen is right above the carbon group on the chart. So CO2 is going to have a -2 oxidation state for oxygen. So oxygen is going to be
Is the carbon group isn't even out there, on the chart, right?
that's right, yeah. So it would be even lower. I was thinking 7. It's group 4, so that's going to be not even on the chart. So if oxygen is -2, what does carbon have to be to add up to the overall charge? Close. +4, because there's 2 oxygens and they're -2 each. So it has to be +4 so that the overall thing is 0. What about in carbon monoxide? What's oxygen? Still -2. And what's carbon here? 2. +2. So if you have something that, let's say, converts carbon monoxide to carbon dioxide, like a catalytic converter in a car, that's one of the things that it does. That's an oxidation reduction reaction. You're oxidizing the carbon by going from +2 to +4. And in that case, you're reducing something else, but yeah. All right, so let's practice these. We know all these types of reactions now. So let's look at how we can determine which one is which and which type is which and what the products would be. So first, let's stick with oxidation reduction for a minute. I'm just going to give you a reaction and ask you to determine if it is or is not an oxidation reduction reaction. We don't have any simple, like, obvious elemental substances here. So we can't just say, oh, there's a pure element, so that one's got to be a redox. So how do we determine if this is a redox reaction or not? What do we have to do?
You look at the charts.
Yeah, you have to assign oxidation states to each element on each side, and then see if anything's changing or not. So take a look at your chart. I can't quite get it all the way on there, but there's no fluorine in here anyway. Try to, assign oxidation states for each element on each side of that equation, and then decide, is it a redox reaction or not?
I think so.
I'm not sure where to start on one of those. So what kind of oxidation states did you come up with? Sorry to cut you off, but we're almost done. So, what are the oxidation states for oxygen on the left? We got 3 things on each side: O, S, and H. Oxygen's -2. What about hydrogen? +1. Hydrogen's always going to be +1 except when it's with a metal. That's the only difference, because the metal gets priority and has to be positive, so then hydrogen can be negative. And what about sulfur then? What does sulfur have to be? +6. Because SO3's got 3 oxygens. They're all -2, so 6. So 3 times 2 is 6. So sulfur must be +6 to offset those oxygens. All right, what about on the right? What's oxygen? So we've only got 1 compound here, so we have to follow the list. We have to assign hydrogen first, then oxygen, and then we go down and assign sulfur. So oxygen is -2. Or I'm sorry, hydrogen has to be +1, oxygen has to be -2. So what does sulfur have to be to balance in that particular compound? Yeah, still +6. So hydrogen is +1 and there's 2 of them. Oxygen is -2 and there's 4 of them. So that makes -6. And then we need +6 on the sulfur. So is it redox? No, because there's no change in oxidation states. So that's how you determine if an equation is a redox equation or not. In terms of predicting redox equations, you really can't, or at least not in the way that we're doing some of the other ones. So that's why we didn't really focus on that. But you should be able to identify them, figure out what the oxidation states are and what's changing and what's oxidizing or being oxidized or being reduced. All right, so please get started on the Chapter 4 homework if you haven't already, because that test is going to come fast. Come with questions on Thursday. That'll be our last chance to kind of discuss and practice before the exam on Monday.
Were you really learning any? Were we learning?
Oh, hold on a second before you go. Lab tomorrow is the chemical reactions lab, so make sure you look for that. There is some pre-lab work to do. It's actually good practice on this stuff. It asks you to write the reactions for all the different things that we're going to be doing. So take a look at that, and let's see you in lab tomorrow.
Are we learning anything Thursday, or is Thursday a giant review day?
Do we ever learn anything? I don't know.
Well,
Yeah,
like,
because they were also doing Chapter 5.
Okay. Oh, okay. It's not just a whole big review day.
No.
Okay.
Yeah, we got to get into Chapter 5 too, or we're going to get behind.
Okay.